In this lecture, we want to discuss Bernoulli's equation. Um, so this is lecture 4 from the section on linear ordinary differential equations. Bernoulli's equation is a nonlinear first-order equation, and it's a special nonlinear first-order equation that can be transformed into a linear equation by making a specific transformation. So first of all, let's remember what a linear first-order ordinary differential equation looks like. Basically, it will contain the first derivative of y, and this is assuming the equation is in the form of y as a function of x. So it'll contain the first derivative of y, and it'll contain a y, and then you'll have some function of x, possibly that after you do some manipulation and get the first derivative term without a coefficient, multiplies y, and you might also have some function of x that does not multiply y. If this r is equal to 0, then you have a homogeneous equation. If the r is not equal to 0, you have an inhomogeneous differential equation. So Bernoulli's equation is very similar, except we've replaced r of x with just a different function of x, g of x. And notice that that multiplies y to the power a. So this a is not a derivative, it's an exponential. Now, if the constant term a is 1 or 0, the equation is linear. And if g of x is 0, as we said before, the equation is both linear and homogeneous. So Bernoulli's equations form a special family of equations that are fairly common in engineering. And so it's something that definitely you may either already have encountered or you may encounter in the future. So the goal here is to transform Bernoulli's equation into linear form. And we do that by making a substitution for y with the function u of x. And u of x, so this exponent a is going to prove to be very important because what we're going to do is we're going to set u of x to be y of x to the 1 minus a power. Now, if we take the derivative of this, then using the exponent rule, we'll bring down the 1 minus a power. Y will then be raised to the power of 1 minus a minus 1, which is just minus a. And then we take the differential of y, so we'll have a y prime. So this is the derivative u prime. Now notice that here we could solve for y prime. So we have a relationship between y prime and u, and we have a relationship between y and u. So if we come back to our original differential equation, here for y prime, I want to come back to my equation for y prime, my original differential equation, and I'm going to substitute what y prime is equal to for this y prime in my u expression. So when I do that, I get the following using the product rule of differentiation. And then a little bit of algebraic simplification, combining some y terms, I get the following for u prime. And so I have my 1 minus a here. Now, having done that, coming back up to my definition of u, where y to the 1 minus a is equal to u, I can substitute a u for this term right here. And when I do that, then that's going to yield the following differential equation after some simplification. And so you can see what we have here is we have a linear ordinary differential equation in u. So just as an example, let's let those functions of x be constants. We'll just work a relatively simple example. And so here is my differential equation in y prime, and the first thing we want to do is we want to put that in the form where we have y prime minus a function of x times y is equal to a function of x times y to the n, y to the a. So this is just the modified form, doing some algebra. And now we can identify that a, our exponent on y, is equal to 2. So u, which is y to the 1 minus a power, is going to be y to the minus 1. So if we take the derivative then of u prime, we'll get minus y, and I'm sorry, this should be a minus 2 times, it's a typo, times y prime. And then if we substitute for y prime from our original differential equation, we get the following equation, and then some simplification gives us b minus a to the y minus 1. So all algebra here, and please make a note, I'll fix this in the PowerPoint slides, but I'm leaving it in the video. This 2 should be a negative exponent. Okay, the last term is minus a to the y minus 1, and based on our definition of u, that's minus au. So if we make some substitutions for y to the minus 1, then we have the following equation. So this is a linear inhomogeneous equation with a constant b. So that shows you how to transform this differential equation from a differential equation that's nonlinear in terms of y into a linear equation in terms of u. So what we would do here is solve this linear inhomogeneous differential equation in u, and then after the solution is obtained, we can make a substitution to get the solution in terms of y if we so choose. So in doing that, here is our differential equation in u repeated. The solution to the linear part, to the homogeneous part. So most of you probably already know this, but when solving an inhomogeneous equation, you always first solve the homogeneous part, and then you solve the inhomogeneous part. And so this is a very standard, classic differential equation. If we let b equal 0 and solve the homogeneous equation, we get an exponential where c is a constant of integration, and a is whatever the constant was in the equation. So to determine the solution to the inhomogeneous part, you basically have to have a solution that will work in the differential equation. So being that this is a standard differential equation form, the solution to the inhomogeneous part is well known to be b over a. So the general solution is the homogeneous solution plus the inhomogeneous solution. And we get that to be this c e to the minus at plus the constant b over a. Now, we can find the solution for y by remembering the relationship between y and u. U was y to the minus 1, so y is u to the minus 1. So basically, we can set y equal to 1 over u and obtain the following solution for this differential equation. Notice here that we're working with y in forms of t, which is y is a function of t, which is fairly common when you've got exponential forms. It's also very common in electrical engineering. So we will talk a lot more about homogeneous and inhomogeneous solutions and general and particular solutions in the following lectures, but this is a fairly well-known part of differential equations, that you find a homogeneous solution and an inhomogeneous solution, and that the net solution is the sum of the two. Okay, so that concludes this lecture on Bernoulli's equation, and it pretty much concludes everything that we will do that's coincidental with Chapter 1 in your Craysid book. So the next set of lectures will focus on material from Chapter 2.